Okay, everybody, Dr. D here again. This is your Chapter 5 video. This chapter is kind of complicated, so the video should be short because we're only covering part of the chapter, and there's only so much I can do in a video when the topics are this advanced. So, what we're looking at doing is introducing VSEPR, talking about steric number, bond angles and lone pairs, and getting a feel for the shapes of molecules. VSEPR stands for valence shell electron pair repulsion. We're going to look at molecular polarity of molecules. We already did in Chapter 4 electronegativity and polarity of bonds. We're going to take that to the next step and look at the polarity of molecules. And lastly, I'll introduce hybrid orbitals. We're only touching on that in the class period. I only do it because I kind of have to. It's what the kind of department decides on a little bit, that we should expose students to that. So why this chapter is important is because the shape of a molecule is critically important. It dictates to a large extent the chemical and physical properties. So we talk about things like, designing a drug or a drug that binds a particular receptor in your body. The shape of that molecule is key in how it binds the receptor. When we talk about toxicology, why certain things are toxic and others are not, or why certain things are toxic to certain animals, not to others, it's because of the receptors. And it's because of that molecular complementarity, and that is the ability of the toxic molecule to fit into a certain receptor. And that is all about the shapes of molecules. That's why this chapter is really important. So, Lewis structures don't really tell us anything about shape. When you think about it, this is a correct Lewis structure for water. Drawing it linearly, say that 10 times fast. But we all know from Chapter 4. Actually, we don't know that yet. So that's a correct Lewis structure. But I might have mentioned it, and that's why I say that in Chapter 4 last times I mentioned this, but water is not linear. It's actually bent. But Lewis structures don't show that, because that is an acceptable Lewis structure. In class, I might have drawn it lots of times like this, knowing that it's bent. But either of those are correct Lewis structures, okay? They don't really show you shape Lewis structures. So that's what's key about this chapter. So here's the valence shell electron pair repulsion theory. And the idea is it's kind of like balloons. That's what are used here. If you grab all these balloons by their nipples and hold them, they're all going to kind of orient themselves in space. You can think of those balloons as electron clouds maybe, and orient themselves in space to minimize that electron repulsion. They want to kind of space themselves out. That creates a lower state of energy, creates it more stably. So if you have 6 balloons, they can have 4 around that equatorial area and 2 pointing out, 1 top, 1 bottom in these axial positions. Okay? So that is just certain ways of doing it and certain ways of looking at it. And these are the steric numbers. It's basically the number of attached. It's basically the number of regions surrounding the central atom, if you will. 2 regions, 3 regions, 4 regions, 5 regions, and 6 regions. You can't have 1 region, because then if you have only 1 atom surrounding a central atom, it's obviously only linear. You can only have, HCl has to be linear. So there is no Sn equals 1. So to use VSEPR theory, you must first determine the number of electron pairs. So we call this electron pair geometry. Some people call it electron domain geometry. It's the total number of electrons surrounding that central atom. And you can get this from the Lewis structure. And that's why I emphasize that Lewis structures are critically important, and that you really can't do much with Chapter 5 if you don't have a good feel for Lewis structures. So the total number of electrons is going to be those ones that are bonded. The ones that are bound by atoms, attached atoms, so in bonds, but also the lone pairs. And electron domain geometry really just describes those arrangements around that of those spatial electron distributions, whether they bonded or non-bonded. Molecular geometry only deals with the atoms that are attached. It doesn't care about the lone ones, because that's what it means when we talk about the shape of a molecule, what's able to bond a receptor and things like that. It's going to be those atoms that are interacting. So here, this is a case where there's no lone pairs, and all the regions around the central atom are atoms. So in this case, the molecular electron pair geometries are the same. So linear is linear, trigonal planar is trigonal planar, tetrahedral is tetrahedral, trigonal bipyramidal is trigonal bipyramidal, octahedral is octahedral. Those names you need to learn. You need to start getting familiar with the angles too. Tetrahedral is 109.5 degrees. And you can see the three-dimensional structure there. I'll bring some models to class so we can see these. Trigonal planar is 120 degrees. If you got something like trigonal bipyramidal, you got two different angles. You got angles between the axial and the equatorial, and then between the equatorial. So these are the case where there is no lone pairs. And if we look at some of these now, we get examples of molecules. Carbon dioxide is linear. BF3, boron trifluoride, is this trigonal planar. Then you got tetrahedral for carbon tetrachloride. And you have PF5 here. And then you have SF6. And they're going to be your trigonal bipyramidal and octahedral. And those are your steric numbers. Now, we can move on to a case where, and I'm just going to do one of these to show you. I'm not going to go through all the steric numbers. So we have a steric number 4. We have a couple options here. We can have all 4 bonded, like we had here, carbon tetrachloride, or we can have maybe one lone pair, and that would be ammonia. Or we can have 2 lone pairs, which will be water. Okay, in this case, they all have the electron domain geometry of tetrahedral, but their molecular geometry is different. So we're only looking at this here. We call it trigonal pyramidal because we're looking at the pyramid. We don't care about the lone pair. You can think of it like that, kind of a pyramid, a three-dimensional pyramid around that central atom. The top is kind of empty, right? We don't care about the lone pairs. We're only describing the molecule itself in terms of the attached atoms. Then you look at water. Water is still tetrahedral electron pair geometry, but the actual molecule is bent because we're not considering this up here. So you ultimately get, when you go through all of these steric numbers, for SN, obviously SN2 is only linear. There is no other option. For SN3, 4, 5, and 6, you get this table, and you get different names, and you start to see bond angles, and you need to get familiar with these names. And of course, our exams are open book, open note, so you don't have to memorize these names. You have to quickly just refer to them. And I'll structure my exams in such a way that you'll have to, draw a Lewis structure, answer a bunch of questions on that structure, and come up with a shape. But you could see here, if there's no lone pairs, then the molecular geometry is the same as the electron domain geometry, electron pair geometry. But then you got a combination here with 6. You got 5, 1. You could have 4, 2. You could have 3, 3. You could have 2, 4. Okay? These are pretty rare, so we don't really discuss these. And here it is for SN5, and you have all these options. Seesaw, because you actually see the model. If I bring it into class, you'll see what I mean by a seesaw, and I'll try to show you that. You got things like T-shaped. Okay? So there's the ammonia and water that we did. And that's what you get out of this. Okay? So now, we talked about electronegativity in Chapter 4, and we realize, which is somewhat obvious now when we think about it, that atoms that are different don't have the same affinity for electrons. And so they don't have the same affinity for electrons within a bond, which is what the electronegativity is, that Pauling scale, is how electrons behave in bonds. So if one atom has greater affinity for those electrons in a bond, it pulls them towards it. This represents a positive sign here, that little plus, and the arrow says, oh, the electrons are being pulled in this direction. So that's one way we notate it. Another thing we do is we go like this. Oh, this has a partial negative charge. and this winds up with a partial positive charge. That's just the symbol delta, the Greek symbol, and it just means partial positive and partial negative. As opposed to something like this, where we say those electrons are fully transferred, and that is a full positive charge and a full negative charge. So, at one extreme, we have nonpolar covalent bonds. At the other extreme, we have truly ionic bonds, where electrons are completely transferred. Most everything else is in between. And we saw the differences in polarity that tell you that bond characterization in Chapter 4. You have to have an electronegativity difference greater than 2 to be considered truly ionic. So most species fall somewhere in between. And lots of times when you think it's ionic because it's a metal and a non-metal, the polarity difference tells you it's actually no, it's a polar covalent bond. And you see things like this. These are polar covalent bonds, okay, because of the electronegativity of differences. Now, you can have polar bonds but not have a polar molecule. If we drew the Lewis structure as linear, you might conclude this is nonpolar, because you'd say that, okay, they cancel each other out. That's the key. Even though carbon tetrachloride has polar bonds, because tetrahedral is symmetrical, all these dipoles get canceled out, and this is not drawn correctly because this is drawn in 2 dimensions, but they do actually cancel each other out, and you might have to take some physics, understand some vector analysis, and realize that, hey, the sum of these 2 vectors is something like this, and that cancels with this one. You have to look at the 3-dimensional molecule. I can't do it on a 2-dimensional page. So that's why water's bent, because we're going to learn that these electron pairs take up more space, so they push the hydrogen atoms down, and that's what makes this molecule bent. The lone pairs wind up here where they can have more space. So you'll learn about spacing of these electrons. You'll learn about bond angles and how they change, because one thing we'll realize is that the bond angles are different. The bond angle in ammonia is no longer 109.5, it's 107. Tetrahedral is 109.5. When you get down to bent, these 2 lone pairs take up even more than this one lone up here, pushes it slightly more down. You wind up at 104.5. So that's the bond angle part of the chapter that's important. Okay, so get familiar with these shapes and molecules, start to learn these tables. The last thing I'm going to talk about, as I said, is a short video. So what we'll learn about in class is the symmetry. Which ones are symmetrical and therefore nonpolar, which ones are not. The last thing is this valence bond theory. And one thing you have to realize is if I bring together 2 atoms and their atomic orbitals, and let's just say this to keep it simple, that once they get close to each other, all that idea of atomic orbitals is thrown out the window because they're going to interact with each other. This nucleus is going to attract these electrons. This nucleus is going to attract these electrons. These electrons are going to repel each other. These dynamic fields. Because remember, what an electron is a wave filling the entire orbital. So you can't think of it as having a bunch of space. It's a wave, just like a sound wave fills an entire room or a light wave fills an entire room. The wave fills the entire orbital. You have this electrodynamic field around the atom, and these interact, and those orbitals go out the window, and you have new dynamic electrical fields forming as the atoms interact to form a molecule. And of course, it would be chlorine gas reacting with hydrogen gas, ultimately, really, to form hydrogen chloride. But you get the idea. The orbitals around these things are going to be changing. So one thing we do to try to figure out what's going on is we do something called this, a valence bond theory. And it come up with this idea of hybridization. It's a way for us to account for things, be able to predict things, be able to explain things. It doesn't necessarily mean it's what's actually happening. We don't actually have to understand how the orbitals shift and rearrange and the energy dynamics of that. We just want to know what the outcome is. And one way to look at this is something like this. We know from experimentation, empirically, and you might know this just by thinking about it logically, but all of those bonds are exactly the same. Well, when you look at carbon, how's it going to form 4 equal bonds when all it has is a filled s orbital and two of the p filled and another vacant p? How the heck does it form 4 equal bonds? Well, all this stuff goes out the window. It recombines. We take the one s orbital that we have, it's a 2s orbital, but I mean a single s orbital, and 3 single p orbitals, and we form 4 new orbitals. We had 4, now we form 4 new orbitals. The 4 new orbitals are identical, and we use an accounting system to say, okay, it formed from the existing s and existing 3 p's, so let's call them sp3 orbitals. And these numbers give you the total, the 3p and the 1s. That's the 4. We wind up with 4 identical sp3 orbitals, and that's what you see here. And that's what the hydrogen will overlap. The hydrogen atom will come in with its orbital, and that'll bond there, bond here, bond here, and bond here. That's what hybridization is. It's a way that we account through this idea of forming molecular orbitals from this idea of valence bond theory, and account for this process. And there you see it here, the hydrogen 1s orbitals overlapping with the 4 sp3 orbitals. So in class, we'll introduce the other hybridizations, not spend much time on it. I'll give you a little quick accounting scheme so that you can answer a question that might be on a final exam, and also prepare you for going into organic chemistry. So when they start talking about it and teaching it, you have at least some sort of foundation. With that, I'm going to conclude the video, and that is the end.